Okay, let's unpack this. Have you ever looked at a complex natural molecule, maybe a potent drug or, a vibrant dye, and wondered how nature, or even a chemist in a lab, builds those intricate ring structures with such, well, exquisite precision?
Yeah. How to get everything exactly right.
Exactly. How do they control every twist and turn, every single bond formed? Today, we're taking a deep dive into a corner of organic chemistry that reveals this secret: concerted paracyclic
A
reactions.
really fascinating area.
Forget the messy multi-step reactions with unstable intermediates that chemists often grapple with. Here, we're talking about seamless, elegant transformations where bonds break and form all at once in one fluid
It's a
motion.
very different picture. No stopping points, just flow.
Right, and this isn't just abstract theory, it's the bedrock of so much modern synthesis, giving us an incredible ability to predict precisely how molecules will behave. We're venturing right into the heart of these reactions, guided by the foundational, almost magical insights of two giants, Woodward and Hofmann.
Their work was absolutely revolutionary. Think about this. By simply looking at the fundamental symmetry of a molecule's electrons, the shapes of their orbitals, basically we can predict precisely how it will react.
Like what product it will form.
Exactly. Even which mirror image product it will form. This stereochemistry. It's like having a crystal ball for molecular transformations. That's the true genius of Woodward and Hofmann.
Wow.
It's a remarkable testament to the power of quantum mechanics in explaining macroscopic chemical behavior, truly allowing us to peek into the intricate dance of electrons and, well, anticipate their every step.
So what does this mean for you listening in? Whether you're a student grappling with advanced organic chemistry or maybe just insanely curious about the hidden logic of the molecular world.
hmm
This deep dive will give you a shortcut to being well-informed on a topic that truly transformed our understanding of chemical reactions. We're essentially giving you a high-level overview of the underlying mechanisms, the core concepts, and the compelling experimental evidence, making what seems like a complex subject accessible and understandable.
Exactly. We'll be exploring the fundamental principles, diving into key reaction types, like the powerful Diels-Alder reaction, the fascinating world of electrocyclic reactions, and even the surprising ways computational chemistry helps us visualize these fleeting transition states.
Those transition states are key, aren't they? The moment of change.
Absolutely. And we'll define all the technical terms plainly, ensuring you grasp the core concepts and can truly appreciate the practical applications in chemical synthesis and analysis. Concerted paracyclic reactions, the big picture.
Okay, so to kick us off, let's nail down what concerted paracyclic reaction truly means. It might sound dense, but the concept itself is actually quite beautiful in its simplicity, almost like a perfectly choreographed ballet.
That's a good analogy.
At its core, a concerted reaction is one that happens without any stable intermediate, so no stopovers.
Right. Imagine a perfectly choreographed dance where bond breaking and bond formation happen simultaneously. Now, it's crucial to understand that simultaneously doesn't mean at the exact same degree or pace.
Uh,
One bond might be slightly more formed than another in the transition state. But the key is, no full-fledged, stable intermediate ever forms that could be isolated or, detected for a prolonged period. It's a single, continuous electronic reorganization.
got it. One smooth move. Now, what makes it paracyclic?
Paracyclic. Think around the circle. This refers to the fact that this reorganization of electrons happens through a cyclic or ring-shaped transition structure.
Like the electrons are flowing around a temporary ring.
Exactly. Much like the path of a paracycle race, maybe. And, critically, this cyclic arrangement must maintain a bonding interaction between the reacting atoms throughout the entire process.
Continuous connection.
Yes, this continuous electronic flow through a highly organized cyclic pathway is what makes these reactions so unique and, as we'll soon discover, so incredibly predictable.
This is where Woodward and Hofmann come in, right? This predictability.
Yeah. This is precisely where their genius lies. They recognized that the pathway of these elegant reactions is dictated by the symmetry properties of the molecular orbitals directly involved, the shapes and phases of the electron clouds.
Okay.
They introduced the revolutionary concept of conservation of orbital symmetry. In essence, this rule states that the symmetry of each participating orbital must be maintained as the reaction progresses.
So the symmetry has to kind of match up.
It has to correlate, yes.
Mhm.
This seemingly simple idea dramatically transformed organic chemistry. Before their insights, many of these reactions were observed, but their precise stereochemical outcomes and patterns of reactivity seemed almost arbitrary, a bit like molecular magic.
You just knew it happened, but not why it happened that way.
Exactly. Woodward and Hoffman provided the why, turning that magic into a rule book and stimulating a huge amount of experimental work to test and extend their theory. This central idea led to other successful interpretations and theories, all converging on the same fundamental conclusion. Transition states, those fleeting molecular arrangements at the peak of the energy barrier, with certain orbital alignments, are energetically favorable, or what we call allowed.
Allowed means they happen easily.
Yes, these allowed pathways lead to fast reactions. Others, conversely, lead to high energy or forbidden transition states, which means they effectively don't happen under normal conditions, too high an energy barrier to climb.
Right.
And what's truly fascinating, this really connects things, is that these allowed stabilized transition states actually share electronic features with aromatic systems, like benzene.
Aromaticity, like the stable rings we talked about before.
Precisely, they exhibit enhanced electron delocalization and a stabilizing ring current. Conversely, the high-energy forbidden ones are more like anti-aromatic systems, unstable.
Ah, okay. So it links back to Huckel's rules and Mobius aromaticity.
Exactly. It links beautifully to the Huckel and Mobius rules for aromaticity that we touched on in a previous deep dive. This connection to aromaticity is powerful because it gives us a simple, intuitive rulebook for predicting outcomes.
Allowed means aromatic-like transition state. Forbidden means anti-aromatic-like basis.
That's a great way to think about it.
Yeah.
And because these reactions go through such highly ordered, specific cyclic transition structures, their outcomes, like the precise stereochemistry of the product, meaning which mirror image form,
So 3D shape.
yes, and regioselectivity, or where new bonds form of the molecule, become remarkably predictable. Even how different substituents affect reactivity can be interpreted directly through their influence on these interacting orbitals and how they stabilize or destabilize that unique transition state.
So we're talking about a fundamental rule book for how electrons can dance and reorganize. It almost sounds too neat, too perfect. Are there ever exceptions or scenarios where these rules don't quite hold up as predicted? And how do we even begin to visualize this dance? Is it purely theoretical?
That's an excellent question. The beauty of the Woodward-Hoffman rules is their robustness. Now, while there might be instances where the mechanism shifts from concerted to stepwise, maybe due to extreme electronic effects or high strain,
So it breaks the rules and goes step by step instead.
well, it finds a different path, usually higher energy. But the fundamental symmetry principles themselves remain valid for the concerted pathway. And no, it's certainly not just theory anymore. Modern computational tools allow us to visualize and map out these fleeting transition structures.
Ah, computers to the rescue.
Indeed. Researchers have employed sophisticated computational methods, particularly density functional theory, DFT, to map out the intricate geometries and energy landscapes of these reactions.
So they can model that split-second transition.
Exactly. And the conclusions from these computational methods generally align perfectly with the orbital symmetry rules, providing a robust validation of the theory. What's more, these computational studies provide additional fine-grained insight into how substituents work their magic, influencing the precise bond formation and electron distribution within the transition state.
Giving us an even clearer picture.
Precisely. So, with that big picture in mind, we'll be focusing on three major categories of concerted paracyclic reactions in this deep dive: cycloaddition reactions, electrocyclic reactions, and sigmatropic rearrangements.
Okay, 3 main types.
The common thread, as we've established, is that concerted mechanism involving a cyclic transition state and the continuous electronic reorganization, all explainable and predictable through the elegant lens of orbital symmetry. Cycloaddition reactions ringing in new bonds.
Let's kick off with cycloaddition reactions. The name pretty much says it all, doesn't it? We're taking 2 molecules and adding them together to form a brand new ring.
Making rings, yep.
Specifically, in concerted paracyclic cycloadditions, the electron clouds, what we call pi-electron systems of the reactants, reorganize to form 2 brand new single bonds.
It's like 2 separate dance teams coming together to form a new unified formation with their peripheral members linking up. That's a good way to picture the pi systems interacting.
We see this with things like the cyclodimerization of alkenes, where 2 simple alkene molecules combine to form a 4-membered ring. Or, most famously and incredibly important in synthetic chemistry, the addition reaction between an alkene and a diene, known universally as the Diels-Alder reaction.
The Diels-Alder, absolutely fundamental.
These reactions are often described by specifying the number of pi electrons each species contributes. So two alkenes adding would be a 2 plus 2 cycle addition because each alkene brings 2 pi electrons.
Makes sense.
And an alkene plus a diene, like in the Diels-Alder, would be a 2 plus 4 cycle addition with the alkene contributing 2 and the diene 4 pi electrons.
Right, 2 plus 4.
Now, here's where it gets really interesting, and where orbital symmetry provides a fundamental, almost surprising insight. Some of these combinations, like the alkenadiene 2 plus 4 addition, happen readily under mild conditions. You warm them up a bit, they react.
Often quite easily.
Yet others, like the 2 plus 2 or alkene cyclodimerization, are almost never observed under normal thermal conditions. Just heating two ethylenes together doesn't give you cyclobutane.
No, it really doesn't. This dramatic difference in reactivity, why one is easy and the other incredibly difficult or impossible thermally, is directly and elegantly explained by the principle of conservation of orbital symmetry.
So symmetry forbids the 2 plus 2, but allows the 2 plus 4.
For the simplest face-to-face approach, yes. This pattern of reactivity is a perfect illustration of orbital symmetry in action. The most important of these, the Diels-Alder reaction, where a diene and an alkene derivative, which we call a dienophile form, a cyclohexene, is a prime example of an allowed reaction.
Allowed and very useful.
It proceeds smoothly, with incredible control over three-dimensional outcomes, and where the new bonds form, making it one of the most powerful tools in a synthetic chemist's arsenal.
You mentioned dienophile. That's the alkene part.
Yes, diene-loving. It's the component that reacts with the diene.
Gotcha.
Another crucial type of 4 plus 2 cycle addition is the 1/3 dipolar cycle addition. These involve systems with heteroatoms, meaning atoms other than carbon, like azazides, nitrones, and even ozone.
So nitrogen and oxygen getting involved?
Right. These specific systems have 4 pi electrons spread over 3 atoms with formal charges and behave electronically like dienes, making their cycloadditions with alkenes, and alkenes also allowed 4 plus 2 reactions. They're invaluable for constructing 5-membered heterocyclic rings.
5-membered rings with N or O.
Exactly, which are very common in pharmaceuticals and natural products.
And the 2 plus 2. You said it was mostly forbidden thermally?
While generally forbidden thermally for a simple face-to-face approach, a few 2 plus 2 cycloadditions are feasible. Notably, reactions involving ketonese compounds with a carbon-carbon double bond connected to a carbon-oxygen double bond can undergo 2 plus 2 cycloaddition.
Ah, ketones are the exception.
They have a special mechanism. We'll explore why this exception exists and how ketones achieve this unusual reactivity later in our deep dive.
Okay, so how does orbital symmetry actually distinguish between the favorable and unfavorable reactions? What's the molecular secret sauce?
It comes down to something called frontier orbitals. The Woodward-Hoffmann principles for cycloaddition reactions were actually formulated in terms of these very specific orbitals.
Frontier orbitals. The edges of the electron clouds.
Sort of. For an energetically accessible transition state, you need proper overlap of the frontier orbitals. These are the highest occupied molecular orbital, or HOMO, of one reactant.
Where its highest energy electrons are.
Exactly. Its most available electrons, you could say. And the lowest unoccupied molecular orbital, or LMO, of the other.
The lowest energy place it can accept electrons.
Precisely. Where it has empty space for new electrons. For cycloadditions, the reactants are generally assumed to approach each other face-to-face, as you'd expect for the parallel alignment of pi electron clouds during bond formation.
Okay, HOMO of one meets LUMO of the other.
Yes, and crucially, their symmetry needs to match for bonding overlap to occur. The rule derived from frontier molecular orbital, FMO theory, shows that the necessary bonding interactions between the HOMO and LUMO are met for 2 plus 4 cycloadditions, leading to a stable transition state.
Good overlap, stable transition state. Allowed.
But I not met for simple 2 plus 2 or 4 plus 4 cycloadditions under a face-to-face approach. The symmetries just don't match up correctly.
Bad overlap, unstable transition state, forbidden.
You got it. More generally, systems involving 4n plus 2 pi electrons, where n is an integer, so 2, 6, 10, and so on, are electronically favorable, or allowed thermally, for a superfacial approach.
6 electrons, like in 2 plus 4, fits the rule.
Right. Conversely, systems with 4n pi electrons, like 4 and 2 plus 2, 8 and 4 plus 4, are electronically unfavorable, or forbidden, for a simple face-to-face thermal approach. This elegantly explains why the Diels-Alder is so common, but combining 2 simple alkenes thermally to make a 4-membered ring is generally not.
That makes sense. A simple rule based on the electron count. But you mentioned something earlier about Mobius topology and the rules flipping. What's that about? Sounds complicated.
Excellent point. It adds another layer, but it's crucial for the full picture. It's about the topology of the transition structure. We can think about Huckel versus Mobius topology, just like we discussed in the context of aromaticity in previous deep dives.
Huckel is the normal flat ring, Mobius is twisted.
Exactly, like a Mobius strip. A reaction can occur where the new bonds form on the same face of the pi system, which we call superfacial, denoted S, or they can form on opposite faces, which is anterofacial, denoted F.
Okay, same side or opposite sides?
To fully specify the topology, subscripts are added to the numerical classification. So you'll see 2s plus 4s for a normal Diels-Alder, indicating superfacial bonding on both the 2-electron and 4-electron components.
Okay.
Now, when you have a Mobius topology in the transition state, think of it like a twisted figure-8 loop of orbitals. Unlike the simple Huckel ring we usually picture, the rules actually flip.
The rules flip.
Yes. Here, 4n pi electron combinations are actually favored, or allowed, and 4n plus 2 pi electron combinations are unfavorable, or forbidden. This is a crucial distinction for understanding the full set of Woodward-Hoffmann rules for cycle additions, which tabulate the allowed or forbidden status for various combinations of superfacial and anterofacial additions based on the total number of pi electrons involved in the cyclic transition state.
So a 2s plus 2a reaction involving 4 electrons but with one component reacting anterofacially would be allowed.
Exactly. That twisted, Mobius-like transition state makes the 4n system stable or aromatic in that context. It's less common because reacting on opposite faces can be sterically difficult, but it's allowed by symmetry.
This is where it really clicks, for me at least. We can actually map this out using something called orbital correlation diagrams, which were another method proposed by Woodward and Hoffmann themselves. Visualizing it helps.
It does. It provides a different perspective on the same underlying principles.
Let's use the classic example. Butadiene and ethene coming together to form cyclohexene in a 2s plus 4 cycloaddition. Normal Diels-Alder. For this to happen in a concerted way, the butadiene needs to adopt a specific cis conformation.
Kind of like a U shape.
Right, and both molecules approach face to face. Crucially, a plane of symmetry perpendicular to the planes of the reacting molecules is maintained throughout this transformation.
Okay, a mirror plane cutting through the middle.
To build a correlation diagram, you classify the molecular orbitals of the reactants, like the pi and pi star orbitals, and the products, the new sigma and sigma star bonds, plus any remaining pi bonds, as either symmetric S or anti-symmetric A with respect to this plane of symmetry.
Matching up the symmetries.
This isn't always straightforward with simple localized orbitals, so we use carefully constructed symmetry-adapted orbitals. But the principle is key.
Right.
When you arrange these orbitals by energy and connect those with matching symmetry, a clear picture emerges. For the 2s plus 4s cycloaddition, all the bonding levels of the reactants, the occupied pi orbitals of ethene and butadiene, correlate directly with ground state product orbitals, the new sigma bonds, and remaining pi bond of cyclohexane.
So occupied orbitals stay in occupied orbitals. No big energy jump needed.
Exactly. This indicates a smooth, energetically favorable pathway.
The conclusion from this orbital correlation diagram is profound. It means the thermal concerted cycloaddition between butadiene and ethene is allowed, and this analysis can be extended. Superfacial additions are indeed allowed for systems with 4n plus 2 pi electrons, but forbidden for 4n pi electrons thermally.
So, different methods, same answer.
Precisely. This consistency across different theoretical methods, frontier orbital analysis, this concept of transition state aromaticity, and orbital correlation diagrams is a hallmark of robust scientific theory. They all lead to the same conclusions about whether a reaction is symmetry allowed or forbidden.
That's reassuring.
And these rules aren't just for simple carbon-only systems. They extend beautifully to charged systems like allylic or pentadenal anions and equations. Crucially, they also apply to isoelectronic systems with heteroatoms.
Isoelectronic meaning same number of electrons, just different atoms.
Right, so you can replace a CTC double bond with CN, CO, NECN, or other multiple bonds, and the same orbital symmetry principles will apply. It's a truly universal set of principles that explains a vast array of chemical reactivity, providing a foundational understanding for so much of organic chemistry. The Diels-Alder reaction, a synthetic powerhouse.
Okay, let's really zoom in on the Diels-Alder reaction. You call it a superstar, a powerhouse. It's an incredibly powerful and efficient way to build 6-membered rings in a single step. So what makes it so special beyond simply being a symmetry-allowed 4s plus 2s cycloaddition?
Well, its reliability and versatility are just immense. As you said, its key features involve an alkene, the dienophile, and a diene coming together to form substituted cyclohexanes.
That six-membered ring.
Yes. And for a concerted reaction, the diene must adopt that specific cis conformation, and the two molecules approach each other in approximately parallel planes, like two dancers aligning perfectly for a complex move. This highly organized transition structure is absolutely critical for the reaction's features.
And one of those key features is its stereospecificity, right?
Absolutely. A defining characteristic is its remarkable stereospecificity. It's a syn, or superfacial addition, for both the alkene and the diene.
Syn meaning same side.
Yes. What does this mean for you in practice?
Yep.
It means if you start with, say, a cis alkene, where substituents are on the same side of the double bond, you get a cis product, substituents on the same side of the new ring. If you start with a trans alkene, you get a trans product.
The geometry is perfectly transferred.
Exactly. We even see this with the simplest possible example, ethene and butadiene, thanks to clever isotopic labeling experiments where deuterium atoms clearly show the stereochemical retention. This exquisite control over three-dimensional outcome is what makes it so invaluable to chemists trying to build complex molecules with specific shapes.
That level of control must have sparked some debate, though. Is it really perfectly simultaneous?
You're right. This high degree of stereospecificity has actually been a central point in the long-standing debate about whether the Diels-Alder is truly concerted or if it involves a fleeting intermediate structure like a diradical.
A two-step process.
Potentially. But the overwhelming consensus, supported by most theoretical analyses, is that the vast majority of Diels-Alder reactions are concerted. If an intermediate existed long enough for bond rotation or inversion to occur, you'd lose that exquisite stereospecificity, and mixtures of products would be observed.
Which you usually don't see.
Which is generally not the case. Now, while these reactions are concerted, the bond formation doesn't have to be perfectly simultaneous at both ends. This is important. In unsymmetrical reactants, one new bond might be slightly more formed than the other in the transition state.
Okay, so not perfectly in sync, but still one step.
Exactly. This is accurately described as an asynchronous concerted process. It's still concerted because no stable intermediate forms. Loss of stereospecificity only occurs if there's a true ionic intermediate where one bond forms fully before the other, allowing rotation. This only happens in extreme cases, typically when reactants are very different electronically, like a strong electrophile and a strong nucleophile, and usually requires more than one substituent of each electronic type.
Got it. Mostly concerted, sometimes asynchronous. Now, beyond the basic ring formation, the Diels-Alder reaction often gives us two different possible stereoisomers, called endo and exo. Why does one often get preferred, especially when the exo product might seem less crowded, less sterically hindered?
Ah, yes, the endo rule. For a substituted dienophile, the substituent can be oriented toward the diene's electron cloud in the endo transition state.
Tuck underneath the diene.
Kind of, yes. Or it can be oriented away from them in the exo transition state, pointing outwards. These two orientations lead to different stereoisomeric products.
Different 3D arrangements.
Exactly. Historically, there's the Alder rule, which states that the endo node of addition is usually preferred, especially when the dienophile has an electron withdrawing group like a carbonyl.
Even if it looks more crowded.
That's what's surprising. The endo product is often more sterically congested. Take cyclopentadiene reacting with dienophiles. It frequently favors the endo isomer, despite the crowding. Even for butadiene reacting with maleic anhydride, a high percentage of product comes from the endo transition state.
So why? Why favor the crowded path?
Well, the Alder rule is a very useful guide. It's important to remember it's not absolute. Mixtures are common, sometimes exo products can even dominate, and the ratio can be highly sensitive to subtle factors like the solvent and even small changes in dienophile substituents.
Like you mentioned, methyl acrylate versus methyl methacrylate.
Precisely. Methyl acrylate with cyclopentadiene gives mostly endo, but if you add just one methyl group to the dienophile, as in methyl methacrylate, the exo product actually predominates. The stereoselectivity predicted by the Alder rule is independent of the overall superfacial requirement, as both endo and exo transition states satisfy that.
So it's not the main symmetry rule. What is it then?
The why of the endo preference isn't about that basic symmetry. It's often attributed to secondary orbital interactions.
Secondary interactions, like extra little attraction.
Exactly. Imagine subtle, stabilizing electronic side attractions between the pi orbitals of the dienophile's attached groups and the developing pi bond in the center of the diene as they come together in that endo orientation.
So the electron clouds just interact a bit more favorably in the endo setup.
That's the most common explanation. These extra attractions tilt the balance towards the endo pathway. Other factors like simple steric effects, electrostatic interactions, and even weak London dispersion forces also play a role in determining that final endo.iso ratio. It can be a complex balance.
Makes sense. What about steric effects just slowing the whole reaction down?
Oh, absolutely. Diels-Alder cycloadditions are also sensitive to steric effects in general. Bulky substituents, whether on the dienophile or at the ends, C1 or C4 of these, of the diene, can hinder the approach of reactants and slow down the reaction rate significantly.
Just getting in the way.
Pretty much.
Okay.
For example, a bulky T-butyl group on 1T-butylbutadiene significantly decreases the reaction rate towards dienophiles compared to a smaller methyl group, clearly showing the steric effect becoming dominant.
Okay.
Another type of steric effect involves interactions within the diene itself. For the diene to react, remember, it must attain that C-cis conformation, the U shape. This can bring substituents at C1 and C4 into close proximity.
Bumping into each other.
Right. So some dienes are much less reactive if they have bulky groups that prevent them from easily adopting this reactive inner shape. Conversely, smaller substituents at C2 and C3 of the diene typically exert little steric influence and can even accelerate the reaction due to electron-releasing effects, or by subtly favoring the C's conformation.
So C2, C3 substituents can help?
Often, yes. But if both C2 and C3 have very bulky groups, like two T-butyl groups, the steric hindrance can be so great that it prevents the diene from ever adopting the Sussen conformation at all, and Diels-Alder reactions of such compounds simply don't happen, completely blocked.
So we've talked about the structure, stereochemistry, and some steric effects. But what about the electronic nature of the molecules themselves? How do electron-donating or electron-withdrawing groups impact these reactions? This seems crucial.
It is absolutely crucial. The Diels-Alder reaction is incredibly sensitive to the electronic character of the substituents. It works best and fastest when the dienophile has electron-withdrawing groups, or EWGs.
Like carbonyls, nitro groups, things that pull electrons away.
Exactly. And the diene has electron-releasing groups, or ERGs.
Like alkoxy groups, amino groups, things that push electrons in?
Right. This complementary electronic nature is key. This is why common dienophiles include things like ketones, maleic anhydride, and nitroalkenes, all with strong EWGs. Unfunctionalized alkenes and dienes react very slowly, often requiring high temperatures. For dienes, ERG substituents, especially at C1, have a particularly strong activating effect.
So you want an electron-poor dienophile and an electron-rich diene for a fast reaction.
That's the classic normal electron demand Diels-Alder.
Yeah.
But this leads us to a fascinating twist. The inverse electron demand Diels-Alder reaction.
Inverse. So the opposite.
Exactly. This is where the roles flip. If the diene is electron poor, maybe it has EWGs attached, then electron-rich alkenes like vinyl ethers and enamines become the best dienophiles.
Okay, so now you want an electron-rich dienophile and an electron-poor diene.
Precisely. And this is beautifully explained by frontier orbital theory. Remember the HOMO-LUMO interaction?
Highest occupied meets lowest unoccupied.
Yes. In normal electron demand reactions, the strongest interaction, the one with the smallest energy gap, is between the diene's HOMO and the dienophile's LUMO. When the diene is electron-rich, its HOMO is high in energy. When the dienophile is electron-poor, its LUMO is low in energy. Small gap, strong interaction, fast reaction.
Makes sense.
For inverse demand, the dominant interaction is between the dienophile's HOMO, which is high energy because it's electron-rich, and the diene's LUMO, which is low energy because it's electron-poor. Again, a small energy gap leads to a strong interaction and a favorable reaction.
So FMO theory explains both types perfectly. What about where the bonds form if both molecules are unsymmetrical? Regioselectivity.
Another area where FMO shines. When both the diene and dienophile are unsymmetrical, there are two possible ways they can align, potentially leading to different regiosomers. The Diels-Alder usually shows a strong preference for specific orientations, often described as ortho and para, like in a benzene ring analogy.
Not met.
Typically not the major product, no.
Yeah.
FMO theory, again, provides the explanation. The reactants prefer to align so that the atoms with the largest orbital coefficients in their respective frontier orbitals, the HOMO of one and the LUMO of the other, are poised to form bonds.
So the electron density is highest where the new bonds want to form?
In a simplified sense, yes. The atoms with the largest contributions to those frontier orbitals line up. This predictive capacity is excellent, guiding chemists in designing reactions to get the specific product they want, although there can be subtle exceptions.
And this relates to charge transfer.
Exactly. Essentially, in these favorable reactions, there's a charge transfer occurring in the transition state. The more electron-rich component acts as a nucleophile, donating electron density, and the more electron-poor component acts as an electrophile, accepting it. Faster reactions generally involve a greater extent of charge transfer, as the HOMO-LUMO gap narrows, further stabilizing the transition state. This is why, very strongly, electrophilic dienophiles, like tetracyanothene, are more sensitive to dinon substituent effects than less electrophilic ones. The charge transfer is more pronounced.
So we've covered the intrinsic nature of these reactions and how their electronic preferences drive them. But chemists aren't content to just let molecules do their own thing, are they? We often look for ways to accelerate and control these reactions, and that's where powerful external factors like Lewis acid catalysts come in. What's the deal with Lewis acid catalysis in Diels-Alder reactions?
You're right, catalysis is huge here. Many Lewis acids, electron pair acceptors, like tin tetrachloride, zinc chloride, various aluminum chlorides, strongly catalyze Diels-Alder reactions, particularly those involving dienophiles with carbonyl groups.
Carbonyls, like in esters or ketones?
Yes. The mechanism of catalysis is quite elegant. The Lewis acid forms a complex with the carbonyl oxygen. It coordinates to that oxygen.
Sticks to it.
Right. This complexation significantly increases the electron withdrawing capacity of the carbonyl group, making the whole dienophile molecule even more electrophilic, a much better electron acceptor.
So it enhances the natural polarity.
Precisely. This enhanced electrophilicity leads to significantly enhanced reactivity and selectivity. The catalyzed reactions proceed much faster, sometimes millions of times faster, and often with enhanced regioselectivity and endo-exostereoselectivity, pushing the reaction towards a desired product even more strongly. This also allows reactions to proceed at much lower temperatures, making them synthetically more practical and often cleaner. Lewis acids essentially promote a higher degree of charge transfer in the transition state.
Can you use them for inverse demand, too?
Yes, Lewis acid catalysis can also be applied to inverse electron demand. Diels-Alder reactions, though in those cases the Lewis acid needs to interact favorably with the diene to make it more electron-poor, activating it towards the electron-rich dienophile.
Okay. And it's not just Lewis acids. You mentioned solvent earlier. Water, surprisingly.
Yes, even the solvent plays a role. While traditional Diels-Alder reactions often use nonpolar solvents like benzene or toluene, it was discovered that water and other highly polar solvents like ethylene glycol can dramatically accelerate some reactions, especially those between relatively nonpolar reactants.
Why would water speed things up? It seems counterintuitive for organic reactions.
It does seem odd at first. It's often attributed to enforced hydrophobic interactions, essentially. The strong hydrogen bonding network of water pushes the nonpolar reactants together, squeezing them out, which increases their effective concentration and forces them to interact.
Like oil and water don't mix, so the oily bits get pushed together.
That's the idea. There might also be specific stabilization of the developing, somewhat polar transition state through hydrogen bonding with the water molecules. It's still an active area of research, but the rate accelerations can be quite dramatic.
Fascinating. So catalysts and solvents give us extra knobs to turn.
Exactly. This ability to fine-tune reactivity and selectivity with catalysts and solvents brings us to the exciting realm of computational chemistry, where we can truly peek into the structure of these fleeting transition states and understand their nuances in detail.
How does computation help here?
Sophisticated computational methods, like DFT, are routinely used to map out the structure and energy of Diels-Alder transition states. This allows us to predict and interpret reactivity and selectivity by comparing the calculated energy barriers for competing pathways, like endo versus exo.
So you can calculate which path is easier.
Yes, and what these computations reveal about synchronicity is fascinating. For simple symmetrical reactants, the bond formation in the transition state is typically synchronous, meaning both new bonds are forming to roughly the same extent. However, for highly electrophilic dienophiles, the transition state can be significantly asynchronous, where one bond is more advanced than the other. This asynchronicity increases with the extent of charge transfer in the transition state, leading to a partial ionic character.
So the more charge transfer, the less simultaneous the bond forming.
Generally, yes. Furthermore, computational studies consistently confirm that Diels-Alder transition states exhibit a kind of aromaticity. There's enhanced electron delocalization of the 6 electrons involved in the bond changes, and their electron distribution often resembles that of benzene.
The transition state itself is aromatic-like.
In a way, yes. An idea first proposed way back in the 1930s. This intrinsic stability of the transition state helps explain the low activation energies of allowed reactions.
Can the models predict the endo-exo ratio?
They can. Computational models can predict exo-endo ratios, often providing good qualitative agreement with experimental observations, helping us understand the subtle energetic differences and the factors influencing these preferences, though the energy differences are often small and can be sensitive to the computational method and solvent modeling.
And Lewis acids, what do the computers say about them?
Lewis acid catalysis is particularly well illuminated by computations. They've revealed profound effects on the transition state. They shift the preference between stereoisomers, often enhancing the endo preference. They significantly increase the net charge transfer to the dienophile, making the catalyzed reactions much more polar. And interestingly, they cause the catalyzed reactions to become less synchronous compared to uncatalyzed ones.
Less synchronous. So the bonds form even more unevenly with a catalyst.
Often, yes. There's also evidence for a stronger secondary orbital interaction between the diene and the complex electron withdrawing group in the catalyzed reaction, which further contributes to enhanced endostereoselectivity. In extreme cases, this strong polarization can even push the reaction mechanism towards a stepwise ionic process, blurring the line with concerted reactions.
Wow. Computation really adds detail.
It does. Computational studies have also shown how electron withdrawing groups on the diene can stabilize the transition state, leading to inverse electron demand. And a powerful way to validate these computational models is by comparing calculated kinetic isotope effects, KIEs.
Measuring how changing an atom's isotope affects the reaction rate.
It's exactly. Comparing calculated KIs with experimental results gives strong support for the proposed transition state structures. Finally, in reactions involving more complex aromatic systems, like polycyclic aromatic hydrocarbons, computational studies have shown that the Diels-Alder process can lead to a gain or redistribution of aromaticity in the product or transition state, significantly influencing reactivity and providing a strong driving force for the reaction, sometimes even involving charge transfer complexes before the transition state.
This really highlights the incredible versatility of the Diels-Alder. So how is it actually used by chemists in the lab, beyond the basics?
Oh, its scope is extremely broad. We've seen how electrophilic dienophiles and electron-rich dienes drive normal reactions, but inverse electron demand reactions are also powerful synthetic tools, sometimes leading to aromatic rings after subsequent elimination steps, which is incredibly useful for building complex fused ring systems efficiently.
Right. But what about clever tricks, using molecules that pretend to be something else?
Yes, that's a key area. One ingenious synthetic application involves using dienophiles that contain what we call masked functionality. These are compounds that react as one thing in the Diels-Alder, but whose adducts can then be transformed into something else entirely, acting as synthetic equivalents of unreactive or inaccessible species.
Like a disguise.
Exactly. For example, chlorocrylonitrile can act as a ketene equivalent. Ketene itself, CH2CO, is tricky to use in 4+2 reactions, but a chlorocrylonitrile reacts readily, and the chlornitrile group in the adduct can then be easily hydrolyzed to a carbonyl group, so you effectively added a ketene unit via the Diels-Alder.
Clever. Any others?
Many. Nitroalkenes are another excellent ketene equivalent. Vinyl sulfones can function as an ethene equivalent. The sulfonyl group can be removed reductively after the reaction. They can even act as equivalents for terminal alkenes. Phenyl vinyl sulfoxide can act as an ethene equivalent, adding an acetylene unit, because its adducts can eliminate benzen sulfonic acid to form a new double bond. Vinyl phosphonium salts can act as alene equivalents. These clever strategies allow chemists to use the power of the Diels-Alder to build structures that would be very difficult to access otherwise.
Amazing functional group transformations hidden within the reaction. What about special dienes?
Absolutely. Beyond simple dienes, certain functionalized dienes are crucial. A famous one is Danishevsky's diene, a specific methoxysiloxybutadiene. Its adducts are trimethylsilydione ethers, readily hydrolyzable to ketones or unsaturated ketones, offering a very controlled route to these important structures.
Very precise.
Another powerful approach involves in situ generated dienes, like oquinodimethanes. These are highly unstable dienes, but they can be generated right in the reaction mixture from stable precursors, often by heating. They are incredibly reactive because their cycloaddition products reestablish a stable benzene ring, providing a huge thermodynamic driving force. These are especially useful in intramolecular reactions. Azobenzofurans are another class of superreactive dienes for similar reasons involving aromaticity gain.
So generating the reactive species only when you need it.
Exactly. Given the highly ordered transition state of the Diels-Alder, it's also a perfect canvas for designing enantioselective reactions, which means controlling the formation of specific mirror image products. This is crucial for pharmaceutical synthesis.
Controlling left-handed versus right-handed products.
Precisely, where often only one enantiomer may be biologically active, while the other could be ineffective or even harmful.
How do you achieve that control?
One strategy is to attach a chiral auxiliary to one of the reactants. This is a molecule fragment with a known 3D shape. This auxiliary guides the reaction to preferentially form one diastereomeric product over the other. These can then be separated, and the auxiliary is typically cleaved off and recovered for reuse. Chiral esters and amides of acrylic acid are often used. Lewis acid-catalyzed reactions often yield the best selectivity here. The auxiliary influences the reaction by steric hindrance or by chelating with the Lewis acid, effectively shielding one face of the dienophile.
So you attach a guide, run the reaction, then remove the guide.
That's one way. A more elegant approach, often preferred now, uses chiral catalysts. These are typically metal ions, like copper or titanium, paired with a chiral ligand, an organic molecule with a specific 3D structure bound to the metal.
The catalyst itself is chiral.
Yes. The metal acts as a Lewis acid, activating the dienophile, while the chiral ligand creates a specific three-dimensional chiral environment around the catalytic site. This forces the reactants to approach in a way that overwhelmingly favors one enantiomeric product, sometimes with greater than 99% enantiomeric excess.
Incredible selectivity.
Many efficient catalysts, including copper complexes with bisoxazoline ligands, box catalysts, and chiral oxazobrylidines derived from amino acids, have been developed. These catalysts often lower the LMO energy of the dienophile and enforce a preferred orientation through a combination of Lewis acid coordination, steric bulk, and even subtle pi stacking or hydrogen bonding interactions between the catalyst and the reactants in the transition state.
Speaking of elegant transformations, what about intramolecular Diels-Alder reactions? Taking a reaction that typically involves two separate molecules and making it happen within a single larger molecule.
The IMDA. Intramolecular Diels-Alder reactions are incredibly powerful for synthesizing complex, polycyclic, multi-ring compounds. You form two new rings in one go, often creating complex bridged or fused systems.
Building complexity quickly.
Yes, and the stereochemistry of the resulting ring junction is precisely determined by the transition state geometry. Beyond the familiar endo-exo preferences seen in intermolecular reactions, the conformation of the chain linking the diene and dienophile within the same molecule becomes crucial. This tether dictates how the two parts can approach each other.
So the connecting chain influences the outcome.
Hugely. This can lead to a preference for cis or trans ring junctions, depending on the number of atoms in the linking chain, the substituents, and the inherent strain in forming the new rings.
Does the synchronicity change in IMDA?
Interestingly, yes. In many IMDA reactions, computational studies suggest the internal bond formation, the one closing the second ring, often runs ahead of the peripheral bond, regardless of the electronic nature of the substituents.
Why is that?
It's thought to be an entropic or proximity effect. The groups are already held close together by the tether, favoring bond formation more easily at the connection point. This contrasts with intermolecular reactions, where electronic effects, HOMO-LUMO interactions, are often the dominant factor controlling asynchronicity.
Proximity wins out. Do catalysts help IMDA?
Oh, absolutely. Just like their intermolecular counterparts, IMDA reactions benefit immensely from Lewis's acid catalysis. This can significantly improve stereoselectivity, control the endo-exo preference, and allow reactions to proceed at much lower temperatures, making them synthetically more practical.
And predicting the outcome.
While electronic interactions largely govern regioselectivity in IMDA, which and connects to which, conformational effects, how the chain prefers to fold, are often the main drivers of stereoselectivity. Since these interactions are highly specific to each molecular structure, molecular modeling, computational chemistry, is frequently used to predict and interpret outcomes. IMDA can also lead to less common structures, like bicyclic rings with strained bridgehead double bonds, and alkynes can be used as intramolecular dienophiles to generate cyclohexadienes. It's a very versatile tool. 133 dipolar cycloaddition reactions beyond carbon-only rings.
Moving on from the Diels-Alder, let's explore another fascinating class, 133 dipolar cycloaddition reactions, or 1,3-DPCA. These are like highly versatile cousins to the Diels-Alder, right? Similar principles.
They are indeed analogous to Diels-Alder, being consorted 4s plus 2 cycloadditions following the same fundamental orbital symmetry rules, allowed thermally.
Okay, 4 plus 2 again. Who are the players here?
They involve a 1003 dipole reacting with a dichlorophyll. The dipolar file is usually an alkene or alkane, just like a dienophile. But the 1003 dipole is different.
What makes it a 1003 dipole?
It's a three-atom system, let's call them ABC, with a four-electron pi system spread across those three atoms, similar electronically to an allyl anion. Crucially, they have at least one resonance structure with opposite formal charges separated by three atoms on A and C, hence the 1003 relationship in the name.
So charges at the ends of a three-atom chain.
In one resonance form, yes. Examples include nitrones with N and O, acides, 3 Ns, diazoalkanes C and 2 Ns, and nitrile oxides, C and O.
Lots of heteroatoms.
Very often, yes. And the dipolar file is typically an alkene or alkane, but really any molecule with a pi bond can work, including carbonyls, amosines, and azo compounds.
What are they good for synthetically?
These reactions are incredibly useful for constructing five-membered heterocyclic rings containing atoms other than carbon. Think of how many drugs contain a five-membered ring with nitrogen or oxygen. These reactions are a fantastic way to build them directly. The products can sometimes undergo further rearrangements like hydrogen schists to form more stable aromatic structures too.
So same rules apply. Orbital symmetry, FMO.
Pretty much. The factors governing 1,5,3-DPCA reactivity, regioselectivity, and stereoselectivity are very similar to what we discussed for Diels-Alder, because it all comes back to orbital interactions and the elegant principle of conservation of orbital symmetry.
Concerted again?
Yes, most 1,5,3-DPCA reactions are considered concerted 2s plus 4 cycle additions, with reactants approaching in parallel planes, similar to the Diels-Alder. There's also evidence from computational studies that their transition states are often aromatic, with a stabilizing ring current primarily involving the 6 electrons undergoing bonding changes, contributing to their favorable reactivity.
Okay, and FMO theory. HOMO meets LUMO.
FMO theory is again key. The most stable interactions occur when the HOMO of one reactant is close in energy to the LUMO of the other. However, here's a bit of a twist compared to Diels-Alder. For some 133 dipoles, both electron withdrawing groups, EWGs, and electron releasing groups, ERGs, on the dipolar file can actually enhance reactivity.
Both. How does that work?
These are called amphiphilic dipoles. It happens because sometimes the HOMO of the dipole interacting with the LUMO of the dipolar file is dominant, like normal demand. Other times the LUMO of the dipole interacting with the HOMO of the dipolar file is dominant, like inverse demand. And sometimes both interactions are significant and contribute to stabilizing the transition state. This can lead to a more complex, sometimes parabolic rate relationship as the dipolar file's electronic character changes.
Interesting. So not always a simple push-pull.
Not always. Other factors also influence reactivity. Strain in the dipolar file, for example, strained rings like Norborn are often more reactive than less strung ones like cyclopentene. And conjugating substituents like phenyl groups also tend to increase reactivity.
Stereospecificity, like Diels-Alder.
Yes, just like Diels-Alder, 1,3-TDPCA reactions are typically highly stereospecific with respect to the dipolar file, meaning the precise three-dimensional arrangement of the starting alkene is retained in the five-membered ring product. This again indicates a concerted process.
And endo-exo.
Similar concepts apply. Different orientations of the reacting molecules can lead to different diastereomers, analogous to endo and exo transition states in Diels-Alder, and there can be preferences depending on secondary orbital interactions or sterics.
Regioselectivity if both are unsymmetrical.
Again, similar principles. For unsymmetrical 1,3 dipoles and dipolar files, two regiosomers are possible. Both steric and electronic factors, particularly FMO interactions, determine the preferred orientation. The strongest interaction usually occurs between the atoms with the largest orbital coefficients in their respective frontier orbitals, providing excellent predictive power.
FMO predicts where the bonds form again.
It does, and extensive computational studies support these FMO predictions, showing lower activation energies for the experimentally observed products. They also reveal details like the earliest transition state, less molecular distortion, often having the lowest activation energy, and being characterized by the lowest dipole moment, reflecting favorable electrostatic alignment. Stronger electron withdrawing groups in the dipolar file generally lead to greater electrophilic character, higher reactivity, and increased asynchronicity in the bond formation, much like in Diels-Alder.
So if we understand these fundamental rules, how do chemists put them to work with 1003 DPCA in the lab? What are the cool applications?
Well, the most obvious application is the direct synthesis of a wide variety of five-membered heterocyclic compounds. That's their bread and butter.
Building those useful rings.
Exactly. But sometimes, the initial 133 DPCA product isn't the final target, but a versatile intermediate. For instance, Pyrazolines, formed from alkenes and diazo compounds, can be subsequently transformed into cyclopropanes through pyrolysis or photolysis, often with the loss of nitrogen gas.
Right.
So the cycle addition sets up a precursor for another ring type.
Using one reaction to enable another.
Precisely. Nitron cycle additions with alkenes are particularly useful. They form isoxazolines. The oxygen-nitrogen single bond in these products can be selectively cleaved by chemical reduction.
Breaking that specific bond.
Yes, and this introduces both an amino group from the N and a hydroxy group from the O in a very controlled, stereospecific way relative to the original alkene substituents. This is a very creative synthetic strategy, effectively allowing chemists to install nitrogen and oxygen functionality along with new carbon bonds simultaneously across a double bond.
Very powerful transformation. Intramolecular versions.
Oh, yes. Just like with Diels-Alder, intramolecular versions of 1-3 DPCA are incredibly powerful. You can generate a 1-3 dipole in situ, meaning right in the reaction mixture within a molecule, perhaps from an anezi or nitron precursor already attached to an alkene. It then cyclizes onto another part of the same molecule, building complex, fused, or bridged heterocyclic ring systems efficiently in a single step.
Generating the dipole on the fly.
Exactly. And another clever variation involves generating 1-3 dipoles from the ring opening of strained three-membered rings like aziridines or epoxides. This ring opening itself is often the rate-determining step and is often a stereospecific electrocyclic process, which we'll discuss next, leading to discrete 1-3 dipole intermediates that then react in the cycle addition.
Wow, connecting different paracyclic types.
Sometimes. Electron withdrawing groups on the aziridine can stabilize the developing negative charge during ring opening, making it easier. Evidence for discrete intermediates in these cases includes reaction rates that are independent of the dipolar file concentration, indicating that the initial ring opening is indeed the slow rate-determining step.
Catalysis. Lewis acids again.
And of course, catalysis plays a big role in 1,3-CPCA as well, often with similar Lewis acids we saw for Diels-Alder, but with some unique considerations. Lewis acids generally enhance the reactivity of the more electrophilic component, just as they do in Diels-Alder, by coordinating to it.
But what's the challenge here?
The challenge is that the 133 dipole itself, especially ones like nitrones, can sometimes be nucleophilic enough at the oxygen to interact with the Lewis acid. This might be detrimental if the dipole is meant to be the nucleophilic partner in the reaction, or if complexation shuts down its reactivity.
So the catalyst might stick to the wrong molecule.
Potentially. One solution is to use highly substituted, bulky Lewis acid catalysts that are sterically hindered and selective for coordinating to the less substituted reactant, often the dipolarophile. For example, bulky aryloxy-aluminum compounds are excellent catalysts for nitron cycle additions, enhancing both reactivity and regioselectivity, sometimes even overriding steric control with electronic control dictated by the catalyst.
Clever catalyst design. What do computations show?
Computations confirm that Lewis acids typically complex to the dipole's oxygen atom, for example, nitrogen oxygen, which lowers the energy of the dipole's LMO, enhancing its interaction with the dipolariphile's HOMO. This leads to increased charge transfer and often shifts regioselectivity. These are very similar effects to what we observed in Lewis acid-catalyzed Diels-Alder reactions.
And enantioselective versions. Chiral catalysts.
And yes, absolutely. Enantioselective 1,4-3 DPCA is also possible and highly developed using chiral catalysts, often similar metal ligand complexes to those used for Diels-Alder. These catalysts enforce a preferred orientation of the reagents in the transition state, leading to highly enantioselective products, which is invaluable for drug synthesis where specific stereoisomers are needed. 2+2 cycle addition reactions, the forbidden path.
Okay, we talked earlier about how 2+2 cycle additions, like two alkenes coming together, are generally forbidden for a simple face-to-face approach by orbital symmetry rules under thermal conditions. But then we mentioned an interesting exception, ketenes. How do they pull off this seemingly forbidden reaction?
Right, the forbidden 2+2s. Recall that pathway is symmetry forbidden thermally. However, the orbital symmetry rules state that a 2A+2 cycle addition that's antirofacial for one component and superfacial for the other is allowed thermally.
Antirofacial,
Okay.
attacking from the opposite face. That sounds difficult sterically.
It often is. But this is the unusual topology ketenes often utilize, or at least the transition state geometry resembles this. Ketenes have a linear CCO unit, and the pi orbital perpendicular to the CO bond can interact in an antirofacial manner. An alternative, perhaps more intuitive description for ketone-alkene cycloaddition involves a different type of electronic reorganization that involves 6 electrons overall and ultimately leads to an allowed process with a favorable Hooke-alike topology in the transition state. So there are a couple of ways to rationalize it being allowed.
Either way, ketones find an allowed pathway. What's the transition state like?
The transition state for ketone-alkene cycloadditions is thought to be very asynchronous, much more so than typical Diels-Alder reactions.
Very uneven bond formation.
Extremely. There appears to be a strong initial interaction between the ketone central hybridized carbon and both carbons of the alkene double bond, with significant polar character developing. Electron density is substantially transferred from the alkene, which acts as the nucleophile, to the ketene, which is quite electrophilic, with calculations showing substantial negative charge building on the ketone oxygen in the transition state.
So it's almost like an ionic interaction starts it off.
It has significant polar character, yes. And these reactions show predictable stereoselectivity. The product is a 4-membered ring, a cyclobutano. Usually, the substituents that were on the alkene end up cis to each other in the product. For monosubstituted alkenes, the substituent tends to end up next to and cis to the larger group on the ketone carbon, which is the geometry that minimizes steric interactions in that asynchronous transition state.
Okay, predictable outcome. Why don't ketones do a Diels-Alder with dienes? That's usually preferred.
That's a great question. Surprisingly, with dienes like cyclopentadiene, ketones often prefer the 2+2 cycloaddition over the symmetry-allowed 2+4 Diels-Alder pathway. Computations show a significantly lower activation energy for the 2+2 path in many cases. The polar nature of the ketene seems to strongly favor the asynchronous 2+2 transition state.
Interesting preference. Ketones themselves are pretty reactive, aren't they? Hard to handle.
They are. Given that ketones are often quite reactive and not always stable, they can dimerize or polymerize, how are they handled in synthesis? And what are the applications of this unusual 2+2 pathway?
How do you use them?
Well, the best yields for 2+2 cycloadditions are generally obtained when the ketone has an electronegative substituent like a halogen, which stabilizes it somewhat.
Yeah.
Simple ketones like CH2CO are usually generated in situ.
Made right when you need them.
Exactly. Right in the reaction mixture, because they aren't very stable.
Yeah.
The most common method is dehydrohalogenation of acyl chlorides using a non-nucleophilic base like triethylamine. You basically rip off HCl. They can also be generated by pyrolysis heating to high temperatures of carboxylic anhydrides or even acetone. Interestingly, ketone itself readily forms a dimer, a 4-membered ring lactone, which can then be pyrolyzed, cracked back to generate ketone gas when needed.
Can you do intramolecular versions?
Yes, intramolecular ketone cycloadditions are also possible and synthetically useful when the ketone, or its precursor, and alkene functionalities are correctly positioned within the same molecule, leading to complex fused or bridged bicyclic ketones.
Now, are all 2+2 reactions involving ketones? Or are there other ways to get 4-membered rings?
That's an important point. Not all reactions that look like 2+2 cycloetics form via a concerted pericyclic pathway. Some proceed through discrete zwitterionic intermediates molecules with separate positive and negative charges on different atoms.
So a 2-step process with a charged intermediate.
Right. This typically happens when you combine a very electron-rich alkene, like an animine or vinyl ether, good nucleophiles, with a highly electron-poor electrophilic one, like a nitroalkene or polysanalkene. The first step is nucleophilic attack to form the zwitterion, and the second step is ring closure.
How can you tell the difference?
Stereochemistry is often a clue. The stereochemistry of these stepwise reactions can depend heavily on the solvent. In nonpolar solvents, the ion pair might collapse quickly, retaining stereochemistry. But in polar solvents, the zwitterionic intermediate can live long enough to allow rotation around single bonds before ring closure, leading to a mixture of stereoisomers, a non-stereospecific reaction. That loss of specificity is a clear sign that the concerted pathway is not dominant.
Concerted means stereospecific, stepwise might not be.
Generally, yes. And a very important application of 2+2 cycloaddition, often involving ketones or ketone equivalents, is the reaction with imamine, acetamine bonds, to form the 4-membered volactam ring, also known as an azetonum.
Beta-lactam, like in penicillin.
Exactly. This ring is the crucial structural feature in penicillin and cephalosporin antibiotics. Theoretical studies suggest this reaction, often called the Staudinger synthesis, is typically a 2-step reaction in solution, involving nucleophilic attack of an enolate, derived from the keeping component, on the iminium ion from the enamine, with the second CC bond-forming step often being rate-determining. This reaction has also been used in the stereoselective synthesis of the side chain of the complex anti-tumor agent Taxol, highlighting its utility in building important molecules. Electrocyclic reactions, the molecular turnstile.
Okay, let's switch gears completely now. We've done additions to make rings. What about reactions where a ring opens or closes by rearranging electrons within one molecule? Let's talk about electrocyclic reactions. These are fascinating transformations where a ring opens or closes, and the stereochemistry, the three-dimensional outcome, is incredibly precise.
Yes, electrocyclic reactions are really elegant examples of orbital symmetry control within a single molecule.
So what's the definition?
An electrocyclic reaction involves the formation of a single sigma bond between the terminal atoms of a linear conjugated pi electron system, closing a ring, or the reverse process, breaking that sigma bond to open the ring and reform the linear pi system.
Ring closing or ring opening?
Exactly. A classic example is the thermal ring opening of cyclobutenes to form conjugated butanines. The ring opening of simple cyclobutene to 1,3,3-butanene is an energetically favorable reaction, exothermic, with a moderate activation energy, meaning it happens readily with a bit of heat.
What's so special about it?
What's truly remarkable, and the key observation that led to the Woodward-Hoffmann rules, is the stereospecificity. For example, if you take cis-3,4-dimethylcyclobutene and heat it, it exclusively forms one specific product, Z2,4-hexadiene, only that one isomer of the diene. Essentially, yes. Meanwhile, if you start with trans 3,4-dimethylcyclobutene, the methyl groups on opposite sides of the ring, it exclusively forms the E isomer of the hexadiene. This specificity is extremely high, with almost none of the minor product observed, even if that minor product might be thermodynamically more stable. The reaction only goes one way stereochemically.
Wow. Why such precision?
The reason for this precision is that the groups bonded to the breaking sigma bond rotate in a very specific way during the ring opening. For the cyclobutene opening, a 4-electron process, they rotate in the same sense, either both clockwise or both counterclockwise. This is called the conrotatory mode.
Conrotatory, rotating together.
Yes. If this specific motion is prevented by the molecule's structure, for example, locked in a fused ring system, the reaction requires much higher temperatures and often proceeds through a less selective radical intermediate.
And the reverse reaction, closing the ring.
By the principle of microscopic reversibility, the reverse process, the thermal ring closure of a butadiene to a cyclobutene, must also be chirotatory. Same pathway, just backwards.
Okay, what about other ring sizes? 6-membered rings.
Another important type involves 1,7,3,11,5 hexatrines cyclizing to 1,4,3 cyclohexadienes. This is a 6-electron process. Only specific triene isomers, those that can adopt an cis-X conformation, can achieve the right geometry for cyclization. This ring closure is usually thermodynamically favored due to the formation of more stable sigma bond replacing a pi bond.
And is it stereospecific too?
Yes, these reactions also show high stereospecificity. But crucially, for 1,003,5 trines, a 6-electron system, the groups at the ends of the trine system rotate in opposite senses during cyclization, one clockwise, one counterclockwise. This is known as the disrotatory mode.
It's a rotatory, rotating opposite ways.
Exactly. So 4 electrons go corotatory, 6 electrons go disrotatory, thermally.
So why the difference? Why corotatory for 4 electrons and disrotatory for 6 electrons? This must be where orbital symmetry comes in again.
Precisely. This is where orbital symmetry provides the elegant answer. Woodward and Hoffmann proposed that the stereochemistry of electrocyclic reactions is controlled by the symmetry properties of the highest occupied molecular orbital, HOMO, of the reacting open-chain pi system. The HOMO again. The highest energy electrons dictate the path. Exactly. It's a core idea of frontier molecular orbital FMO theory. Let's consider 4 electron systems, like butadiene closing to cyclobutene. The HOMO of a 1,3,3 called 232, has lobes with opposite phases at its terminal carbon atoms.
Okay, one up, one down at the ends.
If you imagine the signs, yes. For a new sigma bond to form between these terminals, the lobes of the same sign must rotate to overlap constructively. This can only be achieved by a conrotatory motion, both rotating inwards or both outwards to bring same sign lobes together.
Ah, I see. Twisting the same way brings the right parts together.
Exactly. A disrotatory motion would bring opposite phases together, leading to antibonding overlap and preventing sigma bond formation in a concerted way. This applies generally to all thermal electrocyclic processes involving 4n pi electrons, 4, 8, 12.
Okay. Now for 6 electrons, hexatrine.
Now for 6-electron systems, such as 1,305 hexatrines cyclizing to cyclohexadiene, the HOMO, called 3, has lobes with the same phase on the same face of the pi system at its terminal atoms.
Both up or both down at the ends.
Right. To form a new sigma bond, these same phase lobes must overlap. This requires a disrotatory motion, one rotating clockwise, the other counterclockwise, to bring those top lobes or bottom lobes together.
Rotating opposite ways brings the matching parts together here.
Correct. This applies to all thermal electrocyclic processes involving 4n plus 2 pi electrons, 2, 6, 10.
Simple rules based on the homosymmetry. Is there the correlation diagram way to see this too?
Yes. The analysis of electrocyclic reactions can also be done using orbital correlation diagrams. This approach considers the symmetry of all relevant pi and sigma orbitals in both the reactant and product, relative to a symmetry element maintained during the reaction.
Like the mirror plane or rotation axis.
Exactly. If the reactant's ground state occupied orbitals can smoothly transform into the product's ground state orbitals while maintaining that symmetry element, the reaction is allowed and has a low activation energy. If bonding orbitals are forced to correlate with antibonding orbitals, it requires going to a high-energy excited state, so it's forbidden.
Okay.
For the cyclobutene-butadiene interconversion, 4 electrons. If you analyze the disrotatory process, a plane of symmetry is maintained. The correlation diagram shows that bonding orbitals of the reactants would transform into antibonding orbitals of the product, making its symmetry forbidden. High-energy barrier.
But the conrotatory.
For the corrotatory process, a two-fold axis of rotation, C2 axis, is maintained through the center of the breaking-forming bond. Here, the correlation diagram shows that bonding orbitals correlate smoothly with bonding orbitals, so the reaction is symmetry allowed. Low energy barrier.
Matches the FMO prediction. And for 6 electrons.
The same analysis for a hexatrene cyclohexadiene, 6 electrons, shows the disrotatory mode maintains a plane of symmetry and is allowed. Bonding correlates with bonding, while the corrotatory mode maintains a C2 axis and is forbidden. Again, consistent with experiments in FMO.
Okay. And the transition state aromaticity idea, how does that fit?
That provides a third, equally valid perspective. This approach classifies the cyclic transition states as being electronically similar to Huckel or Mobius aromatic-anti-aromatic systems. An aromatic transition state corresponds to a low activation energy, allowed reaction, while an anti-aromatic transition state means a high barrier, forbidden reaction.
So cyclobutene opening, 4 electrons. Conrotatory.
Right. The conrotatory transition state for the 4-electron system has a twist in the cycle of overlapping p orbitals. It has Mobius topology. Mobius systems are aromatic with 4n electrons, so the rotatory path is favored aromatic TS. The disrotatory transition state has Huckel topology, no twist, which is anti-aromatic for 4n electrons, making it forbidden.
And hexatrene closing, 6 electrons, disrotatory.
Correct. The disrotatory transition state for the 6-electron system has Huckel topology. Huckel systems are aromatic for 4n plus 2 electrons, like 6. So the disrotatory path is favored, aromatic TS. The conrotatory transition state would have Mobius topology, which is anti-aromatic for 4n plus 2 electrons, making it forbidden.
All 3 methods agree again. That's really powerful.
It is. Modern computational studies have consistently confirmed these predictions, showing the energetic preference for the allowed modes and even quantifying the activation energies and the aromatic character of the transition states using magnetic criteria, like NICS values. For example, for hexatrene cyclization, the disrotatory transition state is calculated to be significantly lower in energy. Even for 8-electron systems, like octatrene cyclizing to cyclocatrene, which are predicted to be conrotatory. 4n rule, Mobius TS. Computations confirm this helical Mobius-type aromatic transition state.
So the rules hold up across the board.
Yes. All 3 viewpoints, frontier orbital symmetry, orbital correlation diagrams, and transition state aromaticity, converge on the same elegant rules for thermal reactions. Electrocyclic reactions involving 4n plus 2 electrons are disrotatory, Huckel TS, and those involving 4n electrons are conrotatory, Mobius TS.
Okay, so we have the basic modes of rotation, conrotatory or disrotatory. But what about the specific direction of rotation when there are substituents on the molecule? For conrotatory, say, both groups could rotate outwards, or both could rotate inwards, right? Does it always follow the same pattern, maybe to avoid bumping?
That's a very subtle but important question. For conrotatory processes, like in cyclobutene's opening, there are indeed 2 distinct possibilities for a substituent attached to the carbons involved in the ring opening. You can rotate away from the breaking bond, which we call outward, or toward it, rotating inward.
You'd think outward would always be better sterically, less crowded.
You might intuitively think that, especially for larger groups. However, a fascinating observation, backed by experiments and computations, is that some substituents, particularly electron-accepting groups like carbonyls, nitriles, trifluoromethyl, actually prefer to rotate inward towards the breaking bond, leading to a seemingly sterically disfavored product geometry in the resulting dyne.
One word, why would they do that?
The general theoretical analysis reveals that the preference is largely electronic, not just steric. The rule of thumb is donor substituents like NaReO-R and or 2 alkyl groups prefer to rotate outward, while acceptor substituents like NaReCHO-DANO-CF3 prefer to rotate inward.
Donor out, acceptor in. What's the electronic reason?
It's explained by how these substituents interact with the sigma and sigma star orbitals of the breaking CC bond in the transition state. These orbitals become very close in energy, HOMO-LUMO gap shrinks, as the bond breaks, making them good donors or acceptors themselves. Outward rotation provides favorable stabilizing interactions for donor groups interacting with the developing empty orbital, sigma star like LUMO, on the adjacent carbon. Inward rotation allows acceptor groups to have favorable stabilizing interactions with the developing filled orbital, sigma like HOMO, on the adjacent carbon.
Wow, subtle orbital interactions controlling the direction of spin.
Exactly. Computational studies confirm these trends, showing clear energy preferences for inward or outward rotation for various substituents that match experimental outcomes. Interestingly, Lewis acids can increase the tendency for inward rotation of acceptor groups by making the substituent even more electrophilic. In one calculated example, an acyl group switched its preference from outward to inward upon coordination with zinc iodide. These effects on rotational preference also correlate with the overall activation energy of the reaction. The preferred rotation leads to a lower barrier.
Amazing control. Let's bring this to life with some specific examples of electrocyclic reactions, including some very famous and even surprising ones.
Okay. Beyond the initial dimethylcyclobutene example, rigorous studies on cis and trans 3,4,4-dichlorocyclobutene confirm the expected conrotatory opening to give specific isomers of dichlorobutadiene. And consistent with the stereoelectronic effects, the trans isomer, where both chlorines can rotate outward, has a lower activation energy, reacts faster than the cis isomer, where one chlorine is forced to rotate inward.
Makes sense. What about that divorbenzene you mentioned?
Divorbenzene, a particularly intriguing case. Bicyclo 2.2.0-hexa-2-palamo-5-dene. This is a valence isomer of benzene, same atoms, different connectivity. For a long time, it was thought too unstable to exist because benzene is so stable. But stable derivatives were eventually isolated, and even the unsubstituted benzene was finally made in the 1960s.
But it's much higher energy than benzene.
Much higher. And it has a highly strained central CC bond, yet it's kinetically stable at room temperature. Why? Because its conversion to benzene via a concerted thermal electrocyclic pathway would require a conrotatory ring opening. It's a 4-electron cyclobutene ring opening.
Conrotatory, 4n electrons.
Right. But this conrotatory process would lead not directly to stable benzene, but to a highly strained, unstable cis-cis trans-cyclohexatrine, ZZ-cyclohexatrine. A direct disrotatory pathway, which would lead smoothly to benzene, is symmetry forbidden for a 4-electron thermal reaction.
So the easy path is blocked by symmetry.
Exactly. Computational studies confirm a significant energy barrier, around 25-30 kilocoulomb, for its thermal transformation to benzene, allowing its isolation and study. It beautifully demonstrates the power of these symmetry rules in explaining kinetic stability versus thermodynamic stability.
What about valence tautomerism? You mentioned that briefly.
Another fascinating example is the rapid equilibrium often seen between cycloheptatrienes and their bicyclic isomers, bicyclo 4.1.0-hep2,4-odenes, which have a cyclopropane ring fused. This is a very fast electrocyclic transformation happening readily even below room temperature with a very low activation energy, maybe around 7 kilopal.
So the ring is constantly opening and closing.
Effectively, yes, under the right conditions.
Yeah.
This is called valence tautomerism. The fact that the ring geometry already holds the reacting ends of the pi system close together reduces the unfavorable entropy of activation, making it fast. This disrotatory opening-closing of the bicyclic form involves the 6-electron pi system of the cycloheptatrine, so its symmetry allowed 4n+2 rule, and geometrically feasible.
Are these used in synthesis much?
Oh yes. Electrocyclic reactions are exploited in synthesis, particularly for the precise construction of specific double bond geometries, like Z-double bonds, which can be hard to make otherwise. We see examples using that inward rotation of formal groups, acceptors, to generate Z-enals. Outward rotation of other substituents is also used strategically. These cyclizations and ring openings are key steps in building complex natural product skeletons, including steroidal systems, often setting multiple stereocenters with high control based on the con or disrotatory rules.
So far, we've focused on neutral molecules, but do these incredibly precise rules apply when we're dealing with charged species like carbocations or carbanions? Does adding or removing an electron change the rules?
That's a key question, and the answer is yes, the rules extend beautifully. The Woodward-Hoffmann rules apply just as well to charged systems, just like the Huckel aromaticity rule, 4n+2, applies to charged rings like cyclopentanediol anion.
Okay, so what's the simplest example?
Probably the interconversion between a cyclopropylcation and an allycation. Breaking the cyclopropane ring involves the 2 sigma electrons of the breaking bond, so it's a 2-pi electron electrocyclic process, formally.
2 electrons, that's 4n+2 with n0, 0, so it should be.
Disrotatory. Orbital symmetry predicts a disrotatory process. Experimentally, simple cyclopropylcations are highly unstable, and their solvolysis, reaction with solvent leads to allyl products, often studied via the solvolysis of cyclopropyl halides or tosylites. Computational studies suggest essentially no barrier to ring opening. It happens concertedly as the leaving group departs.
And is it stereospecific? Disrotatory?
Yes. Just like cyclobutenes show conrotation, substituted cyclopropylications show stereoselective disrotation. For example, studies on cis and trans 2,3-dimethyl cyclopropyl systems show that the reaction rate is dramatically affected by which way the methyl groups have to rotate in the required disrotatory fashion as the leaving group departs. If the allowed disrotatory motion forces the methyl groups to rotate inwards and clash, forming a sterically hindered U-shaped ally allocation, the reaction is very slow. If they can rotate outward smoothly, forming a W-shaped application, the reaction is much faster. This provides strong evidence for concerted, stereospecific disrotatory opening.
Wow, the reaction rate tells you about the rotation. What about bigger charged rings?
Let's look at pentadenylcations, cyclizing to cyclopentanylcations.
Yeah.
The pentadenylcation has 4 pi electrons.
4 electrons, 4n should be.
Corrotatory. This cyclization is exothermic and forms the basis of the synthetically important Nazaroff reaction, which typically cyclizes protonated divinyl ketones, penanones, via intermediate 3-hydroxypentadenylcations. The stereochemistry observed in Nazaroff reactions is consistent with the predicted conrotation. Computational studies show this cyclization can be very facile, sometimes almost barrierless.
Okay. What about anions?
Anionic electrocyclizations also follow the rules. Consider the pentadenyl anion cyclizing to a cycloanyl anion. The anion has 6 pi electrons.
6 electrons, 4n+2 should be.
Disrotatory. Interestingly, these cyclizations are relatively rare, and simple pentadenyl anions are quite stable and don't tend to cyclize easily under thermal conditions. However, examples are known, for instance, in constrained systems like cyclocadmium lithium, where cyclization does occur, and it proceeds with the predicted disrotatory stereochemistry.
And more electrons, say 8.
Good example, the heptadenyl anion cyclizing to a cycloheptadenyl anion. The heptadenyl anion has 8 pi electrons.
8 electrons, 4n should be.
Corrotatory. And indeed, these anions cyclize readily and quite rapidly, consistent with the Woodward-Hoffmann rules, providing further confirmation of their broad applicability to charged systems.
Okay, rules hold for ions too. What about heteroatoms again? Nitrogen or oxygen in the chain?
And finally, yes, electrocyclization isn't just about carbon. What happens when heteroatoms like nitrogen or oxygen are incorporated into these conjugated systems?
Like azotrines or oxytrines.
Exactly. When heteroatoms are part of the pi system, such as in 1-azotrines or 1-oxytrines, they can undergo electrocyclization to form the corresponding heterocyclic rings, like dihydropyridines and purines.
Do they follow the same rules? Disrotatory for 6 electrons?
They do follow the same stereochemical rules, disrotatory for 6 electrons. But interestingly, these heteroatomic systems often have significantly reduced energy barriers compared to their all-carbon analogs. The reactions are often much faster.
Faster with N or O? Why?
For example, 1-oxahexytrine electrocyclization is accelerated significantly by perhaps 105 to 106 times compared to hexatrane itself, even though the reaction might be slightly less favorable thermodynamically.
What's the reason for the speed up?
Computational studies reveal that an unshared pair of electrons, a lone pair, on the heteroatom, actively participates in the reaction, becoming part of the cyclic electron flow in the transition state. This participation leads to a strong preference for outward rotation of groups attached to the heteroatom, e.g., an NH or NR in endosterenes must rotate outwards, and also causes a subtle change in the transition state geometry, making it more favorable. It's this involvement of the heteroatom's lone pair that significantly lowers the energy barrier, accelerating the reaction. It shows how lone pairs aren't always just spectators. Sigmatropic rearrangements, the migrating bond.
Okay, We've explored how rings form via cycloadditions and how they open or close via electrocyclic reactions. But what about when a piece of a molecule, just a group attached by a single bond, decides to pack up and move to a new location within the molecule while the double bonds also shift around? That brings us to our final fascinating class: sigmatropic rearrangements. The name suggests something is moving, but what exactly?
Yes, sigmatropic meaning a sigma bind is changing position, tropopic relating to movement. These are concerted paracyclic reactions where a group initially attached by a sigma bond migrates across a conjugated pi electron system to a new point of attachment. Critically, this migration happens with a simultaneous coordinated shift of the pi electrons within the conjugated system.
So a group hops, and the double bonds rearrange at the same time.
Precisely. It's a concerted shuffle. Sigmatropic rearrangements are described by an IJ notation. This looks a bit different from cycloaddition notation. Here, I and J refer to the number of atoms you count along each fragment from the bond being broken to the bond being formed.
How does that work?
Imagine a bond breaking between atom 1 of the migrating group and atom 1 of the main chain. The migrating group moves, forming a new bond between atom I of its fragment and atom J of the main chain. So, a hydrogen atom migrating I1 across an allyl system to the other end, J3 atoms away along the chain counting start and end points, is a 1-bel-3 shift. A more complex co-rearrangement involves two allyl fragments joining up, breaking one sigma bond and forming another, which is classified as a 3-3 shift.
Okay, Ij tells you how far each part moves. Are there stereochemical things to worry about here too?
Absolutely. Two key stereochemical elements apply, governed by orbital symmetry.
Like contus and disrotatory.
Analogous concepts. First, related to the pi system. The migrating group can stay on the same face of the pi system throughout the migration, which is called superfacial, or it could potentially move to the opposite face, which is anterofacial.
Same face or opposite face again.
Second, related to the migrating group itself. If the migrating group is chiral, like an alkyl group with stereochemistry at the migrating carbon, its configuration can either be retained or inverted during the migration.
So it can migrate with its 3D shape intact or flipped like an umbrella.
Exactly. And just like other paracyclic reactions, the combination of the number of electrons involved, usually 4n or 4n plus 2 in the cyclic transition state, and the topology, superfacial and anterofacial for the pi system, retention inversion for the migrating group, determines if a reaction is allowed or forbidden by orbital symmetry. There are general selection rules derived from orbital symmetry principles for 1J shifts and more general IJ shifts that describe these preferences.
Let's break down the 1J shifts first, where just one atom migrates, often hydrogen or an alkyl group. These seem like good examples.
They are excellent demonstrations of how orbital symmetry dictates what's possible and what's geometrically feasible. Let's consider a 1-for-3 sigmatropic shift of hydrogen.
Hydrogen hopping over one double bond, basically.
Yes. A hydrogen atom moves from one end of a 3-atom pi system, like in propane or an allyl radical patient, to the other end. Frontier molecular orbital analysis suggests this involves the hydrogen's spherical 1s orbital interacting with the pi orbitals, specifically the HOMO or LUMO, often I2, of the allyl system in the transition state.
Okay. Superfacial or anterofacial?
If the hydrogen moves across the same face of the pi system, superfacial, orbital symmetry analysis shows this pathway is forbidden thermally. The symmetry doesn't allow for continuous bonding overlap between the H1s and the allyl pi system in the transition state.
So hopping straight across is forbidden. What about the other way?
The anterofacial mode, where the hydrogen somehow moves from the top face to the bottom face, or vice versa, during the migration, is symmetry allowed thermally. The orbital symmetries match up for bonding.
Allowed, but how does a hydrogen even do that? It seems impossible geometrically.
That's the catch. While allowed by symmetry, the anterofacial 1-vol-3H shift involves an extremely contorted and sterically demanding geometry for the tiny hydrogen atom to bridge across the pi system and move from one face to the other while maintaining bonding. The transition state energy would be incredibly high.
So allowed on paper, but basically impossible in reality.
Pretty much. As a result, concerted thermal 1-vor-3 shifts of hydrogen are generally considered highly unlikely or energetically very difficult, often requiring extremely high temperatures where stepwise mechanisms involving bond dissociation radical formation become competitive or dominant.
Okay, 1-3H shift is basically out. Thermally, what about 1,4,5, hydrogen hopping over two double bonds?
Now, the situation changes dramatically for a 1,4,5 sigmatropic shift of hydrogen. Here, a hydrogen atom moves across a 5-atom pi system, like in 1,4,3 pentaden. This involves the hydrogen 1s orbital interacting with the pi orbitals, like the HOMO-3 of the pentadienyl system.
What do the rules say here?
In this case, the superfacial mode is symmetry allowed thermally. The orbital symmetries match perfectly for a transition state where the hydrogen stays on the same face.
Superfacial is allowed for 1005H. Is it geometrically okay?
Yes. And critically, this allowed superfacial pathway corresponds to a geometrically favorable six-membered ring transition state. The hydrogen can easily bridge across the pi system while staying on one face. This makes thermal 1005H shifts very common and feasible reactions in organic chemistry.
Much easier. What about anterofacial for 1005H?
The anterofacial mode is symmetry forbidden thermally.
So it flips. 1003H is anterofacial allowed, but hard. 1005H is superfacial allowed and easy. What about 1/7?
Good question. For 1007 sigmatropic shift of hydrogen, like in 1005 heptatriene systems, this involves an 8-electron transition state, 4n electrons. Orbital symmetry rules predict the anterofacial pathway to be allowed thermally. And while geometrically challenging, it is observed, for example, in the vitamin D synthesis.
Okay, so the rules alternate based on electron count, like electrocyclic reactions. What if it's not hydrogen migrating, but an alkyl group, like a methyl group? Does it bring its own orbital symmetry?
Exactly. Similar principles apply to migrating alkyl groups, but with the added complexity of retention or inversion of the migrating group's configuration at the carbon atom that's moving. The p orbital or sp3 orbital involved in the migrating CC bond has symmetry that needs to be considered.
So 4 possibilities: superfacial retention, superfacial inversion, anterofacial retention, and terofacial inversion, which are allowed.
Let's look at the common thermal cases based on electron count in the transition state. For a 1-valent-3 alkyl shift, superfacial, this would involve 4 electrons in the cyclic transition state. If the alkyl group migrates with retention of configuration, the topology is Huckel-like, which is anti-aromatic for 4n electrons, making it forbidden. Migration with inversion would be Mobius-like, which is allowed, but superfacial inversion is geometrically difficult. So thermal 1-valent-3 alkyl shifts are generally difficult. For a 1-valent-5 alkyl shift, superfacial, this involves 6 electrons, 4n plus 2, in the transition state. Migration with retention of configuration gives a Huckel-like topology, which is aromatic for 6 electrons, making it symmetry allowed and geometrically feasible. This is observed experimentally. Migration with inversion would be Mobius-like and forbidden here. And 1+N7 alkyl shift, anterofacial. This involves 8 electrons, 4n. Migration with retention gives a Mobius-like topology due to anterofacial plus retention, which is aromatic for 8 electrons, making it allowed, although anterofacial migration is still sterically doing.
Wow, so the allowed pathway depends on electron count, superfacial, anterofacial, A and D retention inversion. Lots to keep track of.
It is, but it follows predictable rules based on achieving an aromatic-like Huckel 4n plus 2 or Mobius 4n transition state geometry that is also sterically accessible. These rules provide a powerful framework for predicting the outcome and stereochemistry of these subtle but synthetically important molecular migrations. Outro.
And there you have it, a deep dive into the fascinating world of concerted paracyclic reactions. From the elegant dance of orbital symmetry governing how rings form in cycloadditions like the Diels-Alder,
To the precise molecular turnstiles of electrocyclic reactions.
and the surprising coordinated migrations of sigmatropic shifts, it's clear these reactions offer incredible predictability and power in organic chemistry.
By understanding these fundamental principles, particularly the conservation of orbital symmetry and frontier molecular orbital theory, we gain profound insights into molecular reactivity and stereoselectivity. It's really a testament to the elegant simplicity that underlies even the most complex chemical transformations.
It really is quite beautiful when you see how the rules fit together.
And as we've seen, computational chemistry continues to provide even deeper insights into these fleeting transition states, validating and extending these foundational rules, and helping us understand the finer details.
So what stands out to you listening in from today's deep dive? Perhaps the sheer elegance of the Woodward-Hoffmann rules themselves, or the synthetic prowess of the Diels-Alder reaction in building intricate ring systems with pinpoint accuracy.
Maybe it's the counterintuitive stereochemistry of electrocyclic reactions, or the subtle control in sigmatropic shifts.
The next time you see a complex ring structure in a natural product or a pharmaceutical, maybe you'll remember the hidden choreography of electrons guided by orbital symmetry that brought it to life.
And there's always more to learn and explore in this field. We've really only scratched the surface today. New variations, new catalysts, and new applications of these reactions are being discovered all the time, continually expanding the chemist's toolkit and our understanding of how molecules can be precisely assembled.
Well, thank you for joining us on this journey through paracyclic reactions. We hope this deep dive leaves you feeling well informed and perhaps even more curious about the wonders of chemistry. Until next time, keep exploring.